The virtual trajectory is called as virtual trajectory because it's not yet something that has been generated by ICUP. For that to happen, there should be a system which synthesizes the motor commands. For example, if you are using the upper body, you need to generate the joint angles and the joint torques in the 17 degrees of freedom in the upper body. So that's the next system, which transforms a virtual trajectory into a real trajectory that is generated by ICUP. For this we use the framework of passive motion paradigm, which was the first article in this series of work published in 2009. The relation between virtual trajectory synthesis system and the passive motion paradigm is similar to the coordination of a movement of a puppet by a puppeteer. So the puppeteer is the virtual trajectory synthesis system. So as the puppeteer pulls the end effector, the rest of the body elastically reconfigures in order to comply to the pull. Or if you try to pull the fingertips of a puppet, once the fingertip reaches the target, the rest of the body has automatically reconfigured in order to allow that end point to reach that goal. This is the idea behind PMP, or passive motion paradigm. And when motor commands or joint angles generated by this process of passive reconfiguration to a pull of a goal is actively fed to the motors or the actuators, then the robot reproduces the movement. So this generates the motor commands and enables ICUP to efficiently track the evolving virtual trajectory, hence generate the real movement. For example, what happens if a virtual trajectory like a mirror image of a sea is fed to the left arm chain of ICUP? We can see in the graph of the end effector space that the ICUP's end effector almost efficiently tracks the evolving virtual trajectory. And at the same time, in the intrinsic space, which is the arm joints and the torso, you get the motor commands in the 10 degrees of freedom. So J6 is the joint 6, J4 is the joint 4. So the left arm torso chain has a total of 10 degrees of freedom. 3 degrees of freedom for the torso and 7 for the left arm. So as the ICUP's end effector tracks the evolving virtual trajectory, you generate also the motor commands in the intrinsic space, and when you feed this to the robot, it actively performs the movement. Now once the robot performs the movement, through proprioception it also gets the trajectory generated by its own end effector. Now comes the question of how do we close the learning loop. It's very simple, because once again you can extract the shape of the trajectory which is generated by your own end effector using the same method that we used to move from trajectory to shape of a teacher's demonstration. We call this as the abstract motor program because this computes the shape of a self-generated movement. And we should note that abstract motor program and abstract visual program can be directly compared to give rise to a learning loop. So when the shape computed by the abstract motor program is similar to the shape in the abstract visual program, you have learned the right parameters to perform that movement shape. Once you have learned to perform that movement shape, you can perform it in any context. For example, if you are turning a screwdriver or a steering wheel or uncorking a bottle of water, you are always performing circular or quasi-circular trajectories. Circularity is a common factor in this, and once you learn one specific example, because of this abstraction in motor learning, you have the implicit potential to both perceive imitate and begin to perform many other skills that share a similar structure. So we basically started teaching ICUB the basic shape critical points like the line, bump and cusp, and then we moved to the rest of the composite shape primitives. So these are some results which are there in the article on the initial trials to learn to produce line, bump and cusp, and these are some scribbles generated by ICUB during the learning process of generating the basics or learning the basics to learn to draw and write in general. While we move to more complex shapes, the basic idea is that since complex shapes can be decomposed perceptually into combinations of primitives, inversely the actions needed to synthesize them can be composed using the combinations of corresponding learnt primitive actions. Once I learn to generate a line, bump and cusp, I can generate a cross or a contact or a peck. If I learn to generate all these things, I can generate a random shape or a pencil sketch and so on, using the previously learned knowledge. So while learning basics, exploration is more important. Exploration or babbling in the space of stiffness and timing, which we have shown that is very little, similar to the optician analogy. And while you are trying to generate more complex trajectories or shapes, composition and refinement of past knowledge is more important because you already have the seeds in place. All you have to do is a little bit of fine tuning to basically generate the right smoothness when you transit from one critical point to another. This can be seen in an example of S. For example, S is a composition of 4 bumps, and this was learnt in just 12 trials, 9 trials. So we can see that initially we already get a good S, and then we move on to slightly lower performance, and in the 9th trial you automatically get the shape with which the learning converges. And these are the trajectories in the end effector space and in the joint space. So what we should observe is that the final motor commands is a matrix of 7500 iterations in time, which is the complete trajectory which represents S, multiplied by 10 degrees of freedom in the left arm torso chain. So you get finally the complete motor command set, which is a set of 75,000 numbers that has to be buffered to reproduce the movement. We also tried other examples like the Gandhi sketch or ICUB's own signature, that is writing its own name, ICUB, and so on. But the basic idea is that once you learn basics, you can use that knowledge in a very systematic way to quickly learn more complex shapes, and these are all context independent. So that was the idea of moving from trajectory to shape and shape to trajectory. You have some knowledge which is independent of the task. So when you impose the context, you basically are able to produce the action without any further complicated learning.